Hello, my name is Carlos. I'm from the University of Sheffield in the UK, and I'm here to talk about communication optimization in distributed spiky neural network simulations. So there's a growing demand for large-scale brain projects, and largely that's why we're here, I suppose, with the Human Brain Project, but also other projects such as the Brain Initiative and so on. So these projects require huge computation behind the scenes, especially when we talk about simulating brain models. So this talk is going to be specifically for spiky neural network simulations in parallel. So just like the sequential counterpart, parallel SNNs, which I'm going to call them from now on, simulations have largely two phases. The update phase, where the state of synapses and neurons is updated based on the equations of the models, and the propagation phase. So the update phase is fairly simple to parallelize because it follows the single instruction, multiple data model, but the propagation phase is a pain on the backside to do. So that's where we focus our efforts on optimization, so making that communication, the propagation of spikes between computational nodes a bit more efficient. So we can see how that, as the number of processes increases, we get an exponential growth on the number of messages and the size of those messages, if we're not careful. So here's how we are trying to be careful about that. So the first approach that we do is do an efficient communication pattern. So when those communication nodes need to send spikes from one to another, we use a point-to-point communication pattern as opposed to an all-to-all communication pattern that standard simulations like Nest and Neuron may use. That's a really, really bad image. So hopefully you can get the point of it. So this is a very simple SNN model, and the boxes are supposed to be representing computation nodes. So obviously we want to spread our neurons into computation nodes so we speed up the process. And when we have, this is depicting a particular propagation phase. So we have spikes happening in this box and in this one. So we need to propagate from here to here and from here to here. So an all-to-all strategy obviously gets very messy very quickly because you have to spread that spike into all of the computing nodes, irrespective of whether they need that information or not. But using that point-to-point, you can target that and reduce communication volume. So another factor that is very, very important, and as we'll see in the next slide, is synchronization events. So even though these two partitions are not really communicating, don't need to communicate on this particular step, they still need to synchronize, i.e. send a blank message saying, dude, I have nothing to tell you, continue with the simulation. So those two factors, if we take them into account and try to optimize them, they speed up synchronization time. Again, you can't see it, but you're going to take my word for it, or come to my poster and we'll discuss it. So here is the all-to-all synchronization time, and those three lines show a significant, drastic decrease of communication time and also in communication volume. And these two here, the red and the green, show a dynamic sparse data exchange communication method, which is supposed to target all those blank messages. They make them a little bit more efficient, and we can see how that really, really impacts simulation. And the other way that we tackle this communication problem, or the scalability problem, is by reducing those messages. So we take a hint from the previous results and we say, okay, can we somehow reduce the need for synchronize to computational nodes? And we use graph partitioning for it. Again, the image is not very good, but I think you can get, this is a complete brain simulation of the fruit fly brain, and what we do is use graph partitioning to minimize the amount of synapses that go between computational nodes. Hence, in the ideal scenario, we won't have any need for synchronizing between partitions. And then we take those clusters and we put them in a computational node. And we see that strategy as well reduces communication size and volume, and also reduces the number of synchronization messages, so the need for synchronizing. And that results in this particular simulation, it was a 10% of synchronization time reduction. So I'm running out of time, but I think I've reached where I wanted to reach. So we've basically shown how parallel SNN simulations, the communication can be improved by doing the communication pattern a little bit more efficient, using particularly dynamic sparse data exchange, and also better neuron allocation by using graph partitioning. And then we have much more work to do, but we could discuss that later. Thank you.